Okay, now let's look at an example where we have the vector field f of xy is negative y comma x, and we're going to calculate the work done along two different paths that start at 1, 0 and end at 0, 1. So first we want the path that moves along a straight line. So in other words, for part A, I just want this path right here. So we're given a description of the path, but not a parameterization for it. And we need that in order to find the line integral. Well, remember a few sections ago we talked about parameterizing some common paths. And a line segment from one point to another is one such path. So remember that if you want the line segment from the point x1, y1 to the point x2, y2, well, there's a common way of doing this. You basically take r of t to be x1 plus x2 minus x1t, and then y1 plus y2 minus y1t, where the range of t values is 0 to 1. Well, let's just talk through that in this case. And in fact, this formula, I think, makes it look more complicated than it really is. More or less the way I think about it is I just think, well, where do I start? I'm starting at the point 1, 0. And then where do I want to be in 1 second? Well, in 1 second, I want for x to go from 1 down to 0. So I want 1 minus t, so that when I plug in t equals 1, I get 0 instead of getting 1. And I want to go from 0 to 1 in 1 second, so there I guess I want plus t. Okay, so there's my parameterization, 1 minus t, comma, well, t. So now we do all the rest of it. Remember, we want to find f of r of t. So I put f in terms of this parameterization here. And f wants negative y in the first spot, so negative t. And then x in the second spot, so 1 minus t. R prime in this case is just negative 1 comma 1. And so f dotted with r prime, negative t times negative 1 is t. And then 1 minus t times 1 is, well, 1 minus t. So we end up just getting 1. And so that means that the work, well, remember the work is the integral along the path. The range of t values was 0 to 1. So the integral from 0 to 1 of this new function 1 dt, well, that's just going to be 1. Okay, so for that first path, we got a work of 1 in whatever units, depending on the units of the force and the units of the coordinates here. Now let's look at part B, where now, instead of taking the direct path, I'm taking a path along this circle here. So here's still the point 1, 0, and still the point 0, 1. So how do I parameterize this? Well, again, for parts of circles, there's a standard parameterization. You essentially just use polar coordinates. This is a circle of radius 1. So r of t will be 1 times cosine t, comma 1 times sine of t. T is just telling you the angle. So in this case, the range of t values is from 0 to pi over 2. We find f of r of t. So f, remember, was negative y comma x. So negative y is negative sine t, comma x is cosine t. R prime is the derivative of all this. So the derivative of cosine t is negative sine t. And the derivative of sine t is cosine t. And so I take the dot product of those two, f dotted with r prime. So negative sine times negative sine is positive sine squared, and then cosine times cosine is cosine squared. So in fact, again, I get the function 1, but now the work isn't the integral from 0 to 1, because the range of t values is 0 to pi over 2. So I end up getting a work this time, which is pi over 2. So let me highlight something very important here, which is that I had two paths. They started and ended the same way. They both started at 1, 0, and they both ended at 0, 1. But they did not give me the same work. Right? So for line integrals, the path actually matters, not just the beginning and the end. Now the thing is, you've probably been trained by certain physical examples to not expect the path to matter. And it's true, there are some vector fields, some very important ones, where the path does not matter. And that's actually one of the things we're going to be talking about next. So for now, though, whenever you're finding the work of some vector field, you have to actually parameterize the correct path, the path that we are discussing, and not just pick any old path.